Right, we're going to talk about energy transfers during phase changes, and these are going to be applied to phase change graphs when there's a change in heat. We have to recall that there are two different types of energy changes, endothermic and exothermic. Endothermic's when energy goes in to that system, and these would be during phase changes like melting, boiling, or what we don't see in our class would be sublimating, going straight from a solid to a gas. And then exothermic is when heat exits that system, when needs to lose heat, would be like when we're freezing or when we're condensing a gas, or when we're depositing, which is going straight from a gas to a solid. Again, we don't see this one really in our class. And all of these are when heat needs to exit or when heat comes out. Then there's also the two different types of energy. We can talk about kinetic energy changes and potential energy changes. Kinetic energy changes are going to be occurring when there's a change in temperature of the system, and that's because kinetic energy is related to temperature and the fact that temperature is the average kinetic energy of the sample. So as the sample heats up or cools down, the energy motion of those particles changes, but that's only happening when there's a change in temperature. Potential energy, on the other hand, is most important to us during the flat phases of our graph, because that's the only kind of energy change occurring when our graph is horizontal or at a plateau or there's no slope to the line. And it's based on the positional relationships of the particles inside that sample. As a solid, those particles are really close to each other. As a liquid, they start to spread out, and as a gas, they're very far apart. So as you go from solid to liquid to gas, the particles move further apart in relation to each other, which is potential energy or positional energy. And again, as we said, this is occurring throughout the whole graph, but we really only care about it during the flat part of our graph. We need to know a few formulas and constants in order to make these calculations work. So kinetic energy equations are going to happen only at the diagonal portions of our graphs, and we should already know delta H, change in heat, is equal to MC delta T. We need to remember that C for liquid water is equal to 1. C for ice and steam, which we haven't really spent a lot of time looking at, are going to be 0.49, and these are all measured in calories per gram degree C. Now, on the other end, when we have flat portions of our graph, we can't use MC delta T because there's no change in temperature. So we're going to use things called heat of fusion and heat of vaporization. For these, it's specific to the phase change that we're discussing. So if we're talking about heat of fusion, that would be solid to liquid. How I like to think about that is going from liquid to solid. When you're freezing, you're fusing that particle together, or that sample together. It's going to fuse together into one. So that's how I remember that that's heat of fusion. And there's a constant called 80 calories per gram. That's the number. That's the fusion constant. And we're going to take our mass times the 80 calories per gram, and that'll give us how many calories change during the heat of fusion process. Heat of vaporization is the other phase change when we're going from a liquid to a gas, or vice versa from a gas to a liquid. And when you make a gas, you're making a vapor. So how much heat does it take to go from liquid to gas to vaporize that liquid? And this number is quite a bit bigger. You're going from 540 calories per gram of substance. And again, these are constants that are specific for H2O. Same thing on the left-hand side for the kinetic energy, the 1 calorie per gram degree C, the 0.49. These are for this is for the substance water. So how do we go about completing these problems? You're going to be given word problems, and we're going to start out by getting the starting temperature and stopping temperature, and we're going to almost always have water involved. So let's just say the starting temperature is minus 10 degrees C and the stopping is 120 degrees C. So then our second step is going to be to draw a graph, and we're going to mark the starting and stopping points on the y-axis. So that's going to look something like this. Stopping at 120, starting at negative 10. And this is in degrees C. Mark any phase change temperatures between the starting and stopping temperatures. So you need to know that the freezing point of water is at 0, and then the boiling point of water is at 100. This doesn't have to be overly to scale. You're just trying to draw these different phases of your graph. At the phase changes, we're going to draw flat lines. So I have one flat line at my 0 and another flat line at the 100. We're going to connect these flat lines to the starting and stopping points. This is going to extend up to the 120. And then I can connect my flat lines like so. And then finally, I can label these 1, 2, 3, 4, 5, because I'm going to need to do 5 different math problems. Typically, the problems that we do in our class, you're either going to do 3 or 5, so be thinking that you're going to need to do an odd number of problems. Do a math problem for each appropriately numbered section of the graph. Use appropriate formulas. So at phase 1, since it's diagonal, I have a delta t equal to 10. And then I need to be thinking c is equal to 0.49 because this is the phase where we're at ice. That's the specific heat of solid water. At 3, my delta t is equal to 100. And my c value here is 1. And then at 5, my delta t is equal to 20, and my c value again is 0.49. Then at the flat sections of our graph, we need to remember if we're at heat of fusion or heat of vaporization. Since this is the freezing point, this is going to be the heat of fusion, which is going to be 80 calories per gram. And then up at 0.4, that's heat of vaporization, which is 540 calories per gram. So we're going to do 5 math problems, 1, 2, 3, 4, 5. All of them are delta H. One, 3, and 5 are going to be MC delta T. And then 2 and 4 are going to be mass times 80, mass times 540. Fill in the appropriate mass as given to you by the problem. And then we filled in delta T, taking 0 and 10, the difference there is 10. And we just know that C, the constant value for ice, is 0.49. Delta T in phase 3 of our graph is 100 because we started at 0, went up to 100. Subtract the 2 values. C is equal to 1. And then delta T for 5 is 20. 120 and 100, the difference is 20. C value there is 0.49.